So like I mentioned, I mean, the first talk will be by me. So by the way, my name is Ville Tuulos. I work here at AdRoll. And this is really about like a product that we started to build basically in the beginning of this year. And we have been, of course, like building these big data products for a long time. AdRoll is all about data. Overall, ad tech is all about data. And like we have been using all kinds of tools. We have been using Hadoop. We are still using Hadoop. We were using Kafka. We are using Kinesis. We are using many different tools in the Amazon AWS stack. And after seeing after going through all these experiences in building these products, I mean, like we kind of recognized a few pain points. And like when we started building this new product, we started to think that, okay, so what are the minimal number of components that we would need to make our life a bit easier this time? And that's why we kind of took a new approach. And it's all about like using Docker, Luigi, and Spot instances to build these really large-scale data workflows. So just to give you some motivation about like what we are really doing here at AdRoll. So AdRoll is an ad tech marketing company. And in this case, the new product that we started to build is really solving kind of one of the key problems in life and universe, and especially marketing, which is that like, well, imagine that like you're like a small startup selling something. I don't know how many of you actually like recognize the device there in the middle. Anyone? No? It's actually, I own one of those. It's called PowerPot. And what it allows you to do is to recharge your mobile phone or whatever device using Campfire. So I mean, you can like go camping and you take the power pot with you and you put some water there, and actually it produces electricity and you can recharge your mobile phone, which is of course the first thing you are concerned when you are camping. So actually they had a Kickstarter campaign, and like it's a nifty device. However, of course they have a slight problem that like not many people know about this thing. So like if you look at that like a green rectangle right there, those are the people who basically bought this device, not too many of them. And then like if you imagine the next rectangle around it, those would be the people who have actually visited the site. And that's a kind of a slightly larger number of people, but I mean still not too many. And then you have everybody else in the world, including you guys, who have never heard about PowerBot before. And of course they would like to sell PowerBot to every single person in the universe, but I mean they have to reach out to them first. And that's what we wanted to solve with the product that we built. So basically looking at the people, what kind of people are interested in this product, and then can we optimize ad targeting for the rest of the people out there so that like they can effectively run their campaigns without bombarding everybody with spammy ads. And now, of course, like how to solve this very kind of a difficult question. Well, I mean, we believe in data. And in our case, we are collecting data from different sources. And you can imagine that in an abstract way, the data is a matrix. Like in this case, on the rows, you have billions of cookies, basically billions of people. And in the columns, you may have like millions and millions of features that you can collect about people and what they are interested in and so forth. And now the green people, or the green rows in this matrix would be people who have bought this device before. And then the yellow might be the people who have visited the site, and then the gray one is everybody else. And now you can imagine that it's possible to come up with an algorithm that looks at the people who have bought this thing before, and then like tries to predict that what's the likelihood of anybody else being interested in this thing. And then you take the people who seem likely to be interested in this product and you show them ads. So that's basically kind of the thing that we wanted to do. Well, of course, now the slight challenge is that the matrix is absolutely huge. So it's really billions times millions. Of course, it's very sparse, so it's still feasible, but it's a large-scale data problem. But I mean, this by itself, I mean, maybe it would be a topic for an academic conference or something, how to do machine learning, but that's not the point. The point is really that like when you are building a modern data-driven product, actually solving the machine learning problem, let's say, is only part of it. So what you need as well is that like you need some kind of, let's say, metrics that you want to present, like, or some kind of analytics that you want to present to your customers in a dashboard. And that's what we did. And also, I mean, of course, like you want to do tons of like ad hoc analytics in the background and analyze that how the product is doing and so forth. So you want to build all these things. So how it works is that like you start with the raw data, like the orange box there at the top. And now you have like these different like data pipelines. So on the left-hand side, for instance, I mean, like you are running the machine learning stuff. You are building the matrix, doing feature engineering. You are building the model. You are applying the model, all that stuff. And then like you may have a different pipeline that actually computes the metrics and does the analytics for the UI. And then you have yet another pipeline that takes care of like all the internal analytics that you want to perform. Let's say you want to push data to Tableau and like whatever is the tool you are using. Well, now the challenge is that these are not independent tasks. They use the same data. They may have like interdependencies. So for instance, in this case, like we actually have some internal analytics things that look at the machine learning models that we have built and all that stuff. So you get this kind of dependency graph. You get this like a kind of a pretty hairy thing. Well, even that would be fine if that's all you had. So in the kind of old days, that there would have been like 5 architects designing this thing, and then like you implement the whole thing. And well, of course, that's not how it works these days. In practice, what happens is that like it's very iterative process. I mean, AdRoll is still kind of a startup. I mean, we don't know. I mean, what we are doing. So we want to kind of keep iterating quickly. So we want to build like kind of different versions of the machine learning model and different versions of the analytics pipeline and different versions of the metrics for the customer. And like what's even like more complicated is that like these different components are built by different people with different skill set, with different backgrounds and different tools that they would like to use. So for instance, in our case, due to the scale, the machine learning component is written by people who know C and like who want to do really low level like machine learning, like Troy somewhere out there. Is she still here? So and like then the analytics, and like we have like a really interesting predictive models that like Brian has been building in R. And then like we have like tons of like internal analytics that basically drives the money side and business side of things that like, for instance, Vincent there has been building. And like these things work with different languages at different scale and so forth. So, well, I mean, of course, like one thing that you could do is that you could tell everybody that, okay, learn Java. I mean, like write your own Hadoop jobs. But I mean, that's really not the fastest way of doing things. So if you think about this, like, of course, you want to build a product like this, like in the fastest possible manner, and you want to operate it in the kind of with the least amount of money, with the least amount of pain, and of course it should be infinitely robust and scalable and in all possible ways awesome. So you want to kind of have all these things, and that this is of course hard, but I mean that's also the reality that like it's a complex thing, multiple people, different skill sets. So how do you manage all this? And now, of course, like kind of like there are like tons of meetups. Like if you write like a big data in meetup.com, I mean like there are all kind of meetups about different frameworks. I mean like Spark is a cool thing today. Hadoop is of course something that kind of a default answer to this question has been for almost 10 years now. And then let's say if you have Python background, I mean there are like tons of cool stuff happening in the Python universe. So there are like definitely like different solutions to this problem. But now the challenge is that, okay, so if you commit to one of these frameworks and you say that, okay, let's write everything using Hadoop or let's write everything using Spark, well, I mean, first, I mean, still you have to solve your business problem. You have to write the machine learning by yourself. You have to design the algorithm. You have to do the feature engineering. And then, of course, still, I mean, you need the infrastructure. You need the instances. You need the, like DevOps people, like keeping Hadoop up and running. And then somehow you need to really do this like a mapping between like how to kind of get all this like a business analytics done on Hadoop or Spark. So it's actually still not the kind of a solved problem, even if you use one of these frameworks. So like one thing that like helps us a lot and like helps many other people out there a lot is that like we are running everything on Amazon Web Services. And the nice thing about Amazon is that like, well, of course these days it's way more than like just EC2 instances. So they have like a DynamoDB as a managed key value store, and especially they have S3, which is basically an infinite storage for your files. So basically, like given that we are so deeply embedded in the AWS ecosystem, we kind of ask ourselves the question that, okay, so what if we basically didn't want to use any of these other frameworks, but like how much we could do just by using AWS? Since the thinking here was that, like, imagine that, like, you wanted to do something like this in a hack day or like a hackathon, and you had like 1 day to get something like this done. So what would you do? I mean, you would probably like launch an EC2 instance, and you would use some like a Python or R or whatever you happen to know, and you would just get it done. I mean, like, yeah, I mean, it's kind of you wouldn't even like kind of try to use some big framework probably. I mean, you just like write a script or something, and that's the fastest way. But now the challenge is, of course, that like, well, I mean, like you can't do that really in a production setting. I mean, that's not what people do. I mean, that would be like horribly chaotic. I mean, like people just like writing hacky bash scripts or something, or like R, God forbid, in production. So that's of course like it's like a huge like the bazaar, like kind of all kinds of crazy stuff that like everybody does. So not really like a production quality, even though it may be fast. Well, I mean, this is of course a kind of a common problem that like kind of the open source community has been facing a long time and so forth. So we kind of like really wanted to think that, okay, so if we embrace kind of this kind of complexity of the word and like, okay, so they are like heterogeneous approaches and so forth, But I mean, we really focused on the speed. So I mean, speed, I mean, there are like tons of like good blog articles by why speed is really important. So we just like get things done as fast as possible while kind of trying to maintain some kind of a sanity that like people can't go totally crazy. But I mean, like if we just like solved a few basic problems for everybody, then we could maybe kind of get this done in actually a way that would be fast, and it still would be like reasonably robust and like reasonably cheap to operate. And kind of the fundamental questions that you want to answer, like if you want to do things in this way, is that first, I mean, like you probably want to kind of normalize the way how people package their jobs. So even if you have one guy using R and the other guy using Python and the third guy using C and so forth, maybe you can somehow package these things like in a consistent manner, so you can deploy them in a consistent manner. And the second thing is that, like, well, I mean, you don't want to bother every single person with their own servers, and like, what if the server goes down and so forth. So somehow you want to manage the resources in a consistent manner. And lastly, you want to orchestrate these different tasks. Like I had that like a dependency graph there, so that like when like you have multiple people writing their own jobs and they are dependent somehow, I mean, like they don't have to coordinate it like at the kind of during lunch hour that, okay, so how we make this work, but there's some like a nice way of making it happen. And now you can of course imagine where I'm going with this. So I mean, like I'm going to quickly kind of provide like answers to all these like 3 questions. And actually, like I said, I mean, this is a product that we built. It's actually in production. We released it in like on June 17th. And like, well, I mean, you can actually like go to our website and like sign up, and like, it's actually unfortunately not like a very like a self-service yet, but if you want to kind of run it like a marketing campaign, it's totally doable. So this is actually something that really works, and it's live and in production, and we have kind of provided a pretty nice solution to these problems. But I mean, this is the main point of this talk, is that you can do it too, and like it's actually really pretty simple to do, especially given the complexity of the underlying problem. And of course, well, I mean, the one of the main key components here is Docker. And the reason why we decided to use Docker is not only that it's like really cool and sexy and so forth, but also for the reason, and especially for the reason that like it's just like it has an amazing community, it has amazing documentation, and it has amazing like tool chain, which really allows people to kind of do these things in a reasonably easy manner. So I used to use OpenVC back in the day, and like actually you can go to openvc.org still, and like you can kind of really see the difference to Docker. I mean, technically it might be the same thing, but I mean, like really the tooling and the documentation makes a big difference. So what we really do with Docker in this context is that, like I mentioned, we have different people who are using different tools. And of course, like you kind of, like when you're using different tools, I mean, you get to this like a dependency hell. That like every tool that you use has different set of dependencies. Even if you use, like if everybody used Python, I mean, you would still get like 50 libraries. And somehow you need to kind of navigate this dependency hairball. So what we do is that like we have these different tasks, like for instance, like the machine learning task, so one part of the machine learning task. And we package it as a Docker container so that it becomes a nice little entity in the Docker repo. It basically provides a contract that this guy is going to provide, let's say, the matrix that's the input for the machine learning model. Or like the matrix is like actually implemented in Python, and the contract is that it actually takes the, let's say, like some input data, and then it produces the metrics in some format in S3, for instance. And the same thing for analytics, that this guy produces CSVs that goes in S3. And then like you don't have to really worry that like what's happening inside. Maybe it's using R, maybe it's using Python. It just works. And now like really the main benefit of this approach is that like, especially going back to that point of like doing things fast while being reasonably robust, is that like we can like leverage all the existing libraries. We don't have to reinvent the wheel, and we don't have to, I know that they are like really cool like machine learning libraries like out there, but let's say like kind of people have been doing these things in R for 10 years. I mean, like that's really battle hardened software, and the same thing goes with Python and especially C. So we can just like keep things simple and just package everything as containers. So that's nice. Well, the second thing is that, of course, as we all know, I assume that like maybe most of you have been using Docker for something before, is that like, of course, the containers don't run themselves. So you need to run them somehow. And of course, the classical solution would be that you have a bunch of servers, and somehow you manage to run these containers on a bunch of servers. And like there are many good solutions out there, like to keep like a microservice type setups running, so that like if instance dies, I mean, like the new one comes up and so forth. But this use case is actually quite different. In this case, we don't have long-running web servers, or we don't have long-running databases. But what we have is that we have these batch jobs that maybe execute minutes, maybe they execute hours in some cases. And when they die, and especially if you run many of them and like you need many instances, you also want to get rid of the instances once you are done, because you don't want to pay for the extra cost. And that's kind of the hard part that like we had to solve. And like, but I mean, it actually makes life much easier like once you have a solution for this. And also another thing that like you can make possible when you have a scheduler like this is that not all jobs are equal. So of course, if you use something like a MapReduce framework, let's say Hadoop, the idea is that you are like traditionally you are living inside the MapReduce paradigm, and you have mappers and like, you have reducers and so forth, and you kind of try to make everything work inside that mindset. And for certain things, it works really fine. So for instance, we have this like a log parsing thing. That's a very classical kind of a MapReduce paradigm. We pull data from Amazon S3 to these different like mappers, which in our case are Docker containers. And we have actually optimized everything so that like we can like pull data super fast from Amazon S3, about like 4 gigabits per second. But I mean, like, let's say when you are talking about like hundreds of terabytes of data, even if you have like one guy pulling 4 gigabits per second, it's going to take like 5 days to pull 100 terabytes if it's only a single box. So you want to have multiple boxes. So you want to run multiple containers in parallel that do this parsing. So it's a pretty classical paradigm. However, now, I mean, the thing is that like there isn't like really like one size fits all approaches. Occasionally you don't want to do things in this way. Occasionally you don't want to actually distribute everything. And like one thing that kind of gets kind of underestimated oftentimes is the beauty of vertical scalability, not horizontal scalability, but the vertical scalability. So which basically means that you, instead of just like having more and more servers running something, you have bigger servers. Maybe you have a single server running something and single big server running something. And like in our case, for instance, the machine learning part of things runs on a big, like the biggest Amazon instance, so like the high memory R3 8x large. And what it means is that like we have really made this so that it's very optimized for this instance type for having like 244 gigabytes of memory. And this is way faster than doing it in any other kind of like a distributed framework, because you don't have to pay for the networking overhead, and you don't have to pay for the serialization overhead or none of that stuff. So it's very like nice that like occasionally you can actually do things in a single box when you want. So really not everything has to be distributed, and like usually that's the flexibility that you lose when you use like one of these like frameworks that kind of force everything to be distributed. So now the kind of like one of the most exciting parts of this thing, and like I'm sure that the Pachyderm guys will be talking more about this, is the fact that I mentioned about like getting these resources. So like I mentioned, I mean there are like 3 problems that we want to solve. The first one was the packaging problem that we solved with Docker, and the second one is the resource management problem, which is that like, well, we are doing this at large scale. We need tons of computing power. It's about like a 10 trillion computations that we want to perform daily, so and it takes a good amount of time and like resources. So we simply can't afford keeping these machines running all the time, although I'm sure that Amazon would be more than happy if we did that. So I mean, like really the approach that you can take, which actually works today in a reasonably good way, and you can actually use the Amazon like Elastic Container Service for this, is that you can actually launch auto-scaling groups. And like if you don't know, auto-scaling groups are just this like a kind of simple entities that Amazon provides that manage a fleet of EC2 instances for you. So you can say that, okay, just like give me always like 5 instances of this type, 5 servers of this type, and if one of them dies, I mean, just launch a new one. And like the only thing that the auto-scaling group does for you by default is that it just ensures that you will always have 5 instances. So what you can do is that like you can like say that, okay, so I know that I'm going to need like lots of memory, so give me high memory instances. And last spring, actually, Amazon released this awesome machine called like D2 8x large that has 24 spinning disks, which has amazing like I/O performance. So if you need anything high I/O, you can just like kind of have an auto-scaling group for those instances and like run everything I/O intensive on those machines, and so forth. And of course, like another beautiful aspect of this is that like you can actually run some of them using spot market, which means that you only pay a low market rate for these instances. But now the main thing, how this thing works in our case, which we have found to be a very useful model, is that we have this thing called like job queue, and it's a very simple queue. And how it works is that like we have a command line tool, and like we have different libraries how you can actually submit a basically a reference to a Docker container to this job queue. Like in this case, you can imagine that we have the log parsing job, or like I mentioned, I mean there are many of them running in parallel, and one of them to the job queue, and we can also to the job queue we can tell that okay, so this job needs to execute on this instance type. And then basically the job queue just like looks what's in the queue and like executes it on one of the server if there's availability. We have a simple like one-to-one mapping between jobs and instances, so there's only one thing running at a time on a single instance. So this is kind of a nice thing. So you just keep like sending jobs to this queue, and when there's availability on the nodes, things get executed. Well, now of course, I mean, like a challenge with this approach is that like what happens if suddenly you get this like a huge, like a big batch of jobs. So suddenly, I mean, like you have 1,000 jobs that you want to execute and you have only like 5 servers. So, well, I mean, you can of course like run 5 at a time and like wait until all of them are done. But the challenge there is that, well, I mean, first, I mean, like it's going to take a long time. And second, I mean, like once everything is done, then you have 5 servers idling. I mean, that's not really optimal either. So what we have today, and like what hopefully you can do by yourself as well, is that like we have this kind of a pretty nice, simple mechanism that actually looks at the queue size, how many containers we have pending, how many containers we have waiting in the queue. And then it actually sends that metric, sends that like a queue size to the CloudWatch, which is this like Amazon service for like tracking metrics. And like there's this nice feature in auto-scaling groups that allows you to take those CloudWatch metrics and connect them to these auto-scaling policies, which basically say that like when the queue grows to a certain size, give me more machines. So every time I have, let's say, 100 jobs pending in my queue, I mean, like let's say that I need let's add like 10 more servers. And as long as there's like a stuff pending in the queue, keep adding servers. And the end result of this is that like, well, you kind of make this auto-scaling group elastic. So basically the more demand there is for a certain instance type, the larger the auto-scaling group becomes, and vice versa. So especially the vice versa part is important, that like when you don't need them, you can kill all the machines. And actually that's the screenshot that I had, where was it? Like here before, so right here. So actually that's like from our like a monitoring system, you can see that it actually like shows you the kind of, let's say, the yellow line or the orange line right there shows that, okay, our queue size increases, and then the yellow line kind of follows it, which is the number of instances. Sorry, I mean other way around. So the orange is the number of instances, and the yellow line is the queue size. So basically we notice that, okay, now we have more demand for instances, launch new nodes. And this is actually like something that like should be like de facto possible using like hopefully Amazon one day. I mean, it's a really nice pattern, and it makes things very cost effective. So that's really the kind of the beauty of it, that like you can really leverage spot instances with this approach. Is the whole point with spot instances is that like you can keep things cheap, but they might go away. With this approach, I mean, like the auto-scaling groups take care of like if the machines go away, you will just get new ones and you keep executing your containers. So yeah, so this is like really nice pattern. Like your jobs are Docker containers, and you get resources through this like very elastic system. Well, now like the last remaining piece that's missing is that, okay, first, I mean, like how do the jobs get in the job queue in the first place? I mean, someone needs to submit them to the job queue. And then the other part is that like, well, I showed you that graph of interdependent jobs, so how do you manage that? So there are like many different solutions to this problem. We are using the one called Luigi. It's actually an open source project. You can like check it out. It's by Spotify. It's a reasonably simple Python server that allows you to kind of define these dependency graphs of jobs or tasks. So if you're going back to this example that I had earlier, so let's say that like you want to execute these different Docker containers. Actually, like kind of the first thing that might come to your mind if you needed to solve this problem, and actually this is something that we did originally as well, is that, well, I mean, you start with like a parse data at like 1 a.m. and you have a cron job. And then like at 2 a.m. you start building the matrix, and like you just hope that everything is done by then. And like 1 a.m. or like 2 a.m. you start compute metrics and so forth, and everything is time-based. And of course it's easy to see that this is extremely fragile. At least it's impossible to ensure that like everything gets executed, especially with this like elastic resources. So you can't do it based on time. You can't use cron. So the next idea that might come to your mind is that, well, I mean, like there are many good systems that actually like allow you to define these dependencies between different jobs. So you could say that first run parse data, and after parse data is done, then like execute build matrix and compute metrics, and then you do build model and so forth. Well, now imagine what happens if you do this, and let's say the build model crashes. So it's the third job in the pipeline, it crashes. So what do? Can you just like restart the build model, or do you have to restart everything from the upstream and like run everything again? And now, especially if you have these like dependencies like all over the place, I mean, how do you know, I mean, what should be run? It gets like very complicated very easily. So even like defining like dependencies between jobs is actually not really the silver bullet. Well, instead, I mean, like what turned out to be a very good idea, and this is something that Luigi supports out of the box, is that instead of defining dependencies between jobs, you actually define dependencies between different data points. So every container, every job produces some output, like the parse data produces parse data, and build matrix produces a matrix. And in our case, these are files in S3. And now instead of saying that parse data or the build matrix depends on parse data, you say that build matrix depends on parse data, like the data file. And build model depends on the matrix that it should get as its input and so forth. And now what happens if, let's say, build model fails? I mean, well, as long as the input that you are expecting is like, let's say in S3, I mean, you can just like restart the build model, and you really don't have to even worry. You don't even have to know about the stuff that happened upstream. So that's really kind of a really nice thing about this approach. And like Luigi makes this very easy. I mean, there are many other good approaches, and like Pachyderm will tell you about one of those approaches. And like how it works is that this is a simple Python class, how you define a task in Luigi. There's a like requires method that basically gives you the inputs. These are the inputs that I'm expecting. And in our case, these are like files in S3. Then there's output. Basically, you promise to produce some output. And then there's like a run method that says that, okay, if this thing doesn't exist, okay, so how to produce it. And in our case, the whole point is, of course, that these outputs are produced by Docker containers. So we basically, this is the guy in the run method that actually like tells that, okay, so this is the Docker container, like in this case, pivot latest tag that we want to execute. And it executes the Docker container, and the Docker container produces the output, and it reads the inputs that it should need. And this way, I mean, we execute the Docker things only when it's kind of really absolutely necessary, which is that like when the promised outputs don't exist, but the inputs exist. And also, like a really important point of this approach, which actually makes a huge difference, is that like this way, actually, this is like really nice solution to high availability. So you might of course ask that, okay, so what happens if the job queue goes down, or what happens if one of the containers die for whatever reason, or one of the servers die that like kind of were running this container? Well, actually it doesn't matter, since I mean the only thing that you say here is that like as long as my output doesn't exist, I mean you keep retrying, and you just keep retrying with this thing until you get what you want. And you don't have to worry about like any other system. I mean everything else can fail as long as your like data is safe, and we use Amazon S3 for this. So like in general, like data is pretty safe there. So this is a really nice pattern, and like it works really in a really like robust manner. And like an additional benefit of this is that like since we are using S3 as our data store, it's like just a big like a hard disk, if you will. So it's super easy to understand. Anyone can take a look and see what files exist. And like if you don't like one file, you delete the file. And so there's no hidden state in a distribution, everything together. Let me just check time. Is that basically we have, like I mentioned, 3 components. First, I mean, like let's say starting from the bottom, I mean we have the Docker containers that basically define one task, one job that we want to execute. They typically produce, or pretty much always in our case, produce a file in S3, goes in S3. And then Luigi basically defines this implicit data dependency graph using S3, and like sees that like if this file exists in S3 and I'm expecting some output, but it doesn't exist, then we can actually execute another Docker container, and it actually like sends the kind of reference to the Docker container in the job scheduler. And then the job scheduler is connected to all the scaling groups that launch new instances when needed. And then finally, I mean, the Docker containers are executed on spot instances, EC2 instances. And so it goes. And like kind of like if you just look at this graph, I mean, it doesn't look too complicated. It's actually not too many moving parts. I mean, Docker is like really familiar to you. I mean, Luigi is an open source tool. I mean, then you just need the scheduler piece there, I mean, which is not too complex by itself. But actually, one thing that's really remarkable about this is that it actually hides a huge amount of complexity. So if you imagine that like we actually have 50 different tasks in our like hairball of dependencies, and they are written in like probably 7 different languages, and they are handling like petabytes of data written by a team of people over a long period of time. So it's just kind of really amazing like what you can actually do with this architecture or a paradigm. So that's really the motivation, and like that's kind of the point of this like meetup as well. So I mean, like, happy to probably answer. I might have some time to answer questions now, and we have like people from AdRoll here who are happy to kind of tell